Nitin and Rohit.
Yes, sir.
So we can start this session. So,
Okay, sir.
let's see. Do you have any particular question which you want me to answer, or you have some comments, or you want to something is not clear? Whatever, we can start. Nitin, you want to start? Nitin, can you hear me? But Nitin, I can't hear you.
Yes, sir. Now I start.
Okay, sure. Perfect. Okay, so please start. If you want to say something about the course, any question, uh, anything about assignments, any topic, you can start. Nitin, can you hear me? Nitin, you are muted. Nitin,
Yes, sir. If you are comfortable, may I speak in Hindi?
हाँ जरूर, कोई प्रॉब्लम नहीं है।
Okay, sir.
हिंदी में भी बात कर सकते हो तुम।
सर अभी हमारे कॉलेज में रोबोटिक्स चल रहा है, मतलब इस सेमेस्टर सेकंड सेमेस्टर में
हाँ
रोबोटिक्स है, तो इसमें फॉरवर्ड काइनेमेटिक्स एंड रिवर्स काइनेमेटिक्स हुआ है इसके रिगार्डिंग। तो इसका थोड़ा डीएच पैरामीटर्स एंड जैकोबियन,
हाँ हाँ।
इनका मुझे थोड़ा फिजिकल मतलब
ओके
अंडरस्टैंड करना था सर।
ओके।
और इसको एक जो डीएच पैरामीटर्स हैं इनको अच्छे से अंडरस्टैंडिंग की सर।
अच्छा, तो आपने कौन सी हमारा नोट्स तो है, इसके अलावा आप कोई कोई बुक्स यूज कर रहे हैं कि नहीं कर रहे हैं?
सर मैंने अभी इसके साथ रोबोटिक इंट्रोडक्शन टू रोबोटिक्स ये यूज
हाँ
किए।
हाँ, तो एक चीज मैं शुरू से ही बताना चाहता हूँ सबको। देखो, जो साहा के बुक है ना, उसका जो कन्वेंशन है, हाँ, वो हमारा कन्वेंशन से अलग है। सो हमारे नोट्स में द कन्वेंशन यूज्ड इज अलग है।
यस
तो
सर।
मैं एक मिनट रुको, मैं दिखाता हूँ कहाँ कैसे यूज कैसे अलग है। I'll share the screen. Just 1 minute. Give me a minute. आपको ये दिखाई दे रहा है? 1 मिनट, मैं स्क्रीन शेयर कर रहा हूँ। ये
ओके
दिखाई दे रहा है?
यस सर।
ओके। तो देखो, एक चीज मैं बताने वाला था। आई कम टू दैट प्लेस। ये दीज आर ऑल इन द नोट्स। ओके।
यस सर।
बट the important thing is this ये picture. Can you see this picture?
यस सर।
Okay. So what happens in, can you see my cursor?
यस सर।
Okay. So what in the convention which I am using, okay, even other conventions also, the joint axis is always along the z axis. ठीक है?
यस सर।
जैसे जैसे ये रोटरी जॉइंट का पिक्चर किया हुआ है जहां पर मेरा कर्सर है। सो
हम्म।
Zi-1 is the I-1 rotary joint. Okay, so Zi is the ith rotary joint. So I plus 1, Zi plus 1 is the I plus 1th rotary joint. So everybody follows this convention most of the time. Okay, the problem is in my convention, the link, ये जो लिंक आई लिखा हुआ है इधर, ये देखो, ये
यस
जो
सर।
मैं हाईलाइट कर रहा हूँ, ये लिंक आई, ये जॉइंट के बाद है।
यस सर।
Okay, but in some books, I think as far as I remember, in Saha's book, the link I is before the joint.
हम्म।
ठीक है? तो इसमें क्या होता है कि वो डीएच टेबल में द link lengths and other quantities are slightly different. So you have to be careful. So if you follow my book, then this is the convention that the link is after the joint. That is one important thing. Once you accept that, then basic ideas are all similar, but just labeling and numbering the joints is different. And also, what happens to the link lengths and other things is also different. ठीक है? ये एक, दिस इज नंबर वन पॉइंट, वेरी इंपॉर्टेंट। हाँ, मैं
यस।
आपको थोड़ी देर के बाद उसका समरी भी बता दूंगा। सेकेंड थिंग इज, any between any two joints, so let's say this I minus 1 and I, there is a common perpendicular. Between any two lines in 3D space, there is a common perpendicular always. Yeah, this is the fact, from geometry. So हमारा common perpendicular is from this line along xi minus 1. So this is zi minus 1, this is xi minus 1. Okay, and wherever they meet, that is the origin of the I minus 1th coordinate system. So you can see here, this is the I minus 1 coordinate system. So for any coordinate system, you have one x-axis, and then you have one z-axis, and you have one origin. So all of these are now defined because I have chosen z along the joint axis, x along the common perpendicular, okay, and the origin is where the common perpendicular is meeting the z-axis. ठीक है?
यस सर।
Okay. So similar is, if you look at this is the link I minus 1. As I said, हमारे convention में the link is after the joint. Okay.
यस सर।
Okay. So now, similar to this link I minus 1, if you see, this is link I here. And similarly, this is the common perpendicular, and this is so on. And this is the origin. ठीक है? इतना तो everybody is using this common perpendicular idea. Everybody is using the fact that the labeling is like this and so on. So once you have this common perpendicular, there are four DH parameters. One of them is this distance along the common perpendicular, which is AI minus 1. Then there is one more, which is this angle between the two z axis. So मैंने क्या किया है इधर, this zi we can zi को we can translate. Okay, we can translate and put it here. So this dotted line is zi. So the angle between zi minus 1 and zi is this alpha. So there is one angle alpha I minus 1. There is one distance ai minus 1. Okay.
Yes, sir. This is twist angle.
Yes, this is alpha I minus 1 is twist angle. ai minus 1 is the link length. ठीक है?
Okay, sir.
Okay. Now there is one more distance, which is this link offset, and there is one more, which is the link rotation. Okay, so in my convention in this, and this is not my, I mean, I didn't invent it. Yeah, John Craig and many other books are it is there. The point is, for link I, there are two variables with subscript I minus 1, एक twist angle and link length, and there are two other variables with di I and theta I. Okay, so this is the important thing. So every time you have a link, any link, if you have, you will have two variables with subscript I minus 1 and two variables with subscript I. ठीक है? Yes, इतना तो I hope it is clear.
Yes, sir.
And the important thing in this convention is the variables have the link I का जो variable है वो subscript I है. Okay, so since it's a rotary joint before link I, so that's why the variable is link. Variable name is theta I. Okay, and if it was a prismatic joint, then the variable length would have been di. Okay, just give me a minute. I will try to connect one iPad and then I can mark also. Just give me a minute.
Yes, sir.
Okay.
Yes, sir. Okay, sir.
Just one thing. So, if the others who have joined, if you have any questions in the meantime, you can type it in the chat box. You can take a look over it as well.
Take minute, please wait. I will come back in exactly 1 minute. I need to open this PDF in another software. So just please wait. एक मिनट, just give me a minute. These are the same lecture notes. Can you hear me, Nitin?
Yes, sir, I hear.
Okay, good. Okay, so I was showing you this.
Yes,
Okay. So what I was trying to tell you is there is one x-axis here, there is one z-axis here, okay, and this is the origin. So for link I minus 1, this is the x-axis, this is the z-axis, and then y-axis is z cross x. Okay. So this is and the whole idea is link I minus 1 is after joint I. So this is joint axis I minus 1. This is joint axis I, and this is joint axis I plus 1. So इसलिए this is link is after the joint, this link is after this. Okay, so as I was saying, so for link I, there are 4 DH parameters. Okay, so one is alpha I minus 1, which is this twist angle. Then AI minus 1, which is length, link length. And then there are this theta I and DI. Okay. So the problem is in any convention that there are some, so these two have I as subscript, and these two have I minus 1 as subscript.
yes, sir.
Okay, so this is confusing to everybody. So in order to avoid this, some people will say, okay, the link is before the joint, then this is labeled as I plus 1, all kinds of things they will do, but you can never avoid this problem. So what I am giving you is this convention where two of them have subscript I minus 1 and two of them have subscript I. The advantage of this convention is in this, out of these 4 DH parameters, आपने भी पढ़ा होगा in Saha's book, 3 are constant.
Yes, sir.
Okay. In this case, what are and 1 is plus 1 variable. Okay, so for link I, the variable is either theta I or di. So at least this I and this I and this I are consistent.
Yes, sir.
So this is the advantage, big advantage of this convention, that the variable for link I has a subscript I.
Yes, sir.
Okay. So this is one, and then there are some other advantages. One is that if you have what is called as a tree structure, this is the only one which works. आपको मालूम है tree structure क्या होता है?
No, sir, but
Okay, I will show you. So once you have this convention, then there are these 4 DH parameters. So as I said, this is important thing is this is for link I, but unfortunately two of them have subscripts I minus 1 and two of them have subscript I.
Yes, sir.
Okay. So let me just show you what is a tree structure and where this doesn't work. Okay, just give me a minute. Give me a minute.
I think if you go to week 8,
Week 8, no? It is in week 8, right?
that
Is it in
articulated
week
body,
8?
that articulated body, yeah. Week 8 slide, slide number 71. No, no, yeah, it's week 8.
Ah. So if you have a structure like this, okay, so there is one fixed node and then it is connected to two arms. So you can think of as like your body. This is what I wanted to show you. So in your body, there are two arms, one and two.
Yes, sir.
Okay, so or if you look at, let's say, the node 7, which is the joint 7. So sorry, if it's, so you don't know where you are coming from. So so for so if your link is before the joint, okay. So uh, this is not this is one way of doing it, but let me just try and find one more simpler way. Ah, okay, I need some more time. I will find it. Don't worry. हाँ, ये दिखाई दे रहा है?
Yes, sir.
Okay, so you see any of these three pictures. So this is the anatomy of a human hand. Okay. So if this is my joint, this is like the palm. Okay. So if the link is after this joint, okay, so from here, you don't know where you are coming from. Sorry, if the link is before the joint.
Zero fixed ground, sir.
So for
Ground.
example, this joint here, okay, you can have one link coming here, or you can have from, so there are
Seven.
many branches which are starting from the same place. So in a tree structure, from this fixed, there are many branches. Okay, so I can easily, following my convention, I can say that this link is after this joint. But if you use Saha's convention, you will have problems.
Okay, sir.
Anyway, so it doesn't matter. It is for as far as this normal things are concerned. Normal things are concerned, it is the same. Okay. So let's go back to this. So this is the DH convention. Is this clear now? I'll show you some examples after this.
Okay, sir. Yes, it is clear.
So there are two quantities which are with I minus 1, and there are two with I, but fortunately these are variables for link I. Okay, so it is good that way. The constants have other subscripts.
Yes, sir.
Okay, and this is an example. Have you seen this example of this Puma robot?
Yes, sir. 560 manipulated.
So Puma 560 robot. So this is my Z1 this way. This is my Z2, which is this way. This is Z3. So the link is after this. Okay. And hence, when you do the DH parameters, so for example, for let's say link 2. So which one is link 2? This is link 2. Okay. So for link 2, you can see that there'll be some distance and some angles. So for link 2, it is pi by 2, 0, 0. Why? Because minus pi by 2, 0, 0, because it is the angle between Z1, which is upward, and Z2. So it is this angle. Okay,
Sure.
so alpha I minus 1 in this example is
Minus pi
270.
by 2.
Yeah, either 270 or minus pi by 2.
Yes.
And what is AI minus 1? This is the distance between Z1 and Z2, that is 0.
Yes,
Okay.
sir.
And then you have theta I, which is this angle theta 1, theta 2, and then you have DI, which is constant. So this is for link 2, the way we have drawn. And this is link 2 after the Z2. Okay. So anyway, so please think about it. It is not very hard, except as I said right in the beginning, the notation for in my notes and in my book or in Craig's book, they are slightly different from what is there in Saha's book and Saha's notes also.
Yes, sir.
Okay, any other question? So this is about DH parameters.
सर थोड़ा जैकोबियन मैट्रिक्स के बारे में, उसका यूज यहाँ पे कैसे करना है, मतलब किस चीज को वो जो फिजिकल मीन होता है वो बताना है।
Jacobian matrix. So you have to give me some time.
Actually, Jacobian will come little bit later. So we are in week 5 right now. So in week 6, so next week Jacobians will come in. So maybe you can wait.
Okay, maybe you can read ahead little bit because all the material is already there. Okay, so but you need to.
The coming week will be velocities and all those things. So
Okay, fine.
that will be you have the Jacobians. So.
Yes, sir.
I need to come out of this. Let me just try to come out of this. No, it's not working. Okay, I will come. I will do this.
So I have stopped. You can directly open Zoom.
So week 6 is Jacobian. Okay, so now let me share the screen. Can you see? Oh no, this is. यह दिखाई दे रहा है आपको? Can you see?
Yes, sir.
Okay. So the basic idea of a Jacobian is that basically I know the angular velocity and the linear velocity of the end effector. Okay. So for example, the angular velocity, this is for a parallel 3R. So this example is for as usual. I have not done it properly. Just give me a minute again. This will come to you. So this is for this robot, planar robot. So this is theta1, this is theta2, and this is theta3. So in this, for this end effector, this is the angular velocity. This is the zero coordinate system, x, y. Okay, you can see no what I have written
This velocity is from the origin, fixed.
from the origin. Yes, from the
Yes.
fixed. That is why this zero is there.
Yes, sir.
Okay, so it's sort of easy to understand that the angular velocity of the end effector will be theta 1 dot plus theta 2 dot plus theta 3 dot about z axis, which is this. And the x and y components will be zero.
Yes, sir.
Similarly, the linear velocity of this point will be this. There'll be some x component, there'll be some y component. And z component will be zero. This is the z component. Okay.
Yes.
So the idea of a Jacobian is that I want to write this linear and angular velocity in terms of joint velocities. So end effector angular velocity and linear velocity in terms of joint velocity. Okay. So ये फिर से एक बार और, this is the angular velocity and this is the linear velocity. So you can see this is a 3/1 vector. This is also a 3/1 vector. So what you want to say is this quantity on this side is v, linear velocity of the tool in zero coordinate system, and this is angular velocity of the tool in the zero coordinate system. And this is given in this symbol means that. And that we can reorganize these are 3 plus 3, 6 equation in this form. So this matrix is called the Jacobian matrix.
Yes, sir. But here end effector is also considered. Then matrix will different.
No, the end effector is being considered. No, L3 is here.
Yes, sir.
So in this picture, this is the end effector. Of course, for this planar example.
Yes, sir.
Okay. So I am trying to write the angular velocity of this end effector. In this case, it is called tool, and also the zero v of this tool. This is the linear velocity. Okay. So this is like a vector 3/1. This is also another vector. So I'm trying to find out both of these. Okay. And at least my claim is that this is the angular velocity of the end effector, and this is the linear velocity of the end effector.
Yes, sir.
Okay, yeah, this is very easy to see. This is also very easy to see because it is nothing but the derivative of the position vector. Okay, so instead of writing like one vector, two different 3/1 vectors, I am going to write it as this is a 6/1 some quantity. This is a 3/1 vector, and this is 6/3 matrix. So this is the Jacobian matrix.
Yes, sir.
Next week it will be taught. So
Okay.
have patience, and then you can see. Okay, anyone else? I see some Ramji.
Good evening, sir.
Good evening. So do you have any question?
Sir, I have taken this course after your introduction in the DMSF smart factories. So
Okay.
I wanted to delve into more depth. That's why I had taken this.
Okay. So which part of the depth you want to see?
Sir,
Which part?
So I was actually trying to delve more into kinematics and workspace.
Okay.
Yes. So what I'm trying to do is develop a visualization tool using this NVIDIA Omniverse
Okay.
to visualize the workspace. So that for that I was just programming on my own.
Okay, very
I
good.
thought, yes.
So how much have you done? So can
Sir, I am
you want to
just,
show us?
Sir, next session I'll try to show.
Okay.
Yes. Thank you.
So basic idea in the workspace, no? At least
Yes, sir.
again, the simplest thing is, this is the simplest idea. Let me just share how you can find the workspace. Okay, so the very deep down, if you go deep down, the workspace comes from inverse kinematics. That is the
Yes.
first important point. Okay. So what is the workspace? Workspace is basically where the inverse kinematic. And of course, I'm taking this planar 3R robot, but all X, Y, phi, end effector position and orientation, where the inverse kinematic solution exists. That is the definition of workspace. And for this 3R case, this is the condition. Okay, and where is it coming from? It is coming from this expression that theta2 is this quantity here, cos inverse of something. So this has to lie between plus minus 1. Cos inverse of 2 is not allowed. Okay, it is not defined.
Yes.
So this has to lie between plus minus 1. And then what is this x and y? If you go back and see the notes, x and y is nothing but the small x and small y minus some L3 cos phi and L3. And L3 is the link, top link length, last link length, and phi is the orientation. So it is basically a family of circles. This is a circle. If you substitute here, what is small x minus L3 cos phi whole square plus small y minus L3 sin phi whole square. So it is like circles with different origins. Okay.
Yes. Yes.
So you have all these different family of circles, and this is what is plotted here. So this is the workspace of this robot. Okay. So it comes from inverse kinematics, and it comes from the condition that the inverse kinematic solution exists. If you take now a complicated one, like let's say this robot, okay, and here also it has something to do with when does the solution exist, okay. And in this case, the solution only exists if that rest point, rest point is O6X, O6Y, O6Z. This is like XYZ of the rest. Okay, so this lies between, this is one sphere, this is a sphere, and this is another sphere, smaller sphere. But in between, there is a cylinder.
Yes.
Okay. So it has to be in between these two spheres, but not on this cylinder. So some point on this place here will also be not in the workspace.
Yes.
Okay, and again, the math is, in this case also, it is not so hard. You can find out easily. But in general, it is not obvious how to find this workspace. So in this case, you can see this is the expression for the workspace. Product of two spheres at different radii. Yes, at different radius. Okay. So in general, in the DMSF course, you saw, no, there was this one talk by Gaurav Sharma. You were there, no?
Yes, sir.
So there are
On
software
ROS.
tools. Yeah, there are
Yes.
software tools which are available, which will give you this workspace very
Yes.
easily. And those are not necessarily you have nice analytical expression. They just do it by trial and error.
Okay.
You can just
Yes.
do forward kinematics. You give values of theta1, 0 to 2 pi, theta2, 0, whatever is joint limits of theta1, theta2, and so on. And then you find out all x, y, z and orientation where it reaches. So that is the way it is done there.
So in effect, we are doing forward kinematics to find all the.
Yes, that is the easiest way to do it.
Okay. Okay.
Okay, so if you do it a very small, step size of the angle, I mean, it will take a lot of time. Okay.
Yes.
So if you do every 1 degree, so it is like 360 to the power 6. But it's not that big a deal nowadays.
Yes.
So you can find the entire workspace. Sometimes you can find analytically, like in this case, two spheres. But not, but see, most of the time you have joint limits. Right now in this example, there is no joint limits. So that's why it is, these two nice spheres are coming. But if you have joint limits, you will have complicated shapes.
The joint limits due to collision.
No, and also
the
because the robot cannot move. Okay.
Okay. Okay.
So every robot, so for example, this robot here, see this robot, no, if you start moving it, it will come and hit here, no?
Yes. Yes.
This theta3, which is about this Z3 axis, it cannot rotate 0 to 360. So there are always joint limits. So there are lots of software. In fact, Nitin, you might be familiar with what Saha is. Someday Saha has a software called Robo Analyzer. Have you used it?
No, sir.
Okay, so if you go to Professor Saha's website or type Robo, I think it's called Robo Analyzer, something like this. In Google, you can search for it. So there also, they do the workspace of many common robots, not all.
Yes.
There is also a free software tool called Robo DK, which is what this other student Ramji was talking about. This is also you can download. And it's free. Free student version is there.
Even MATLAB has like a robotics toolbox. You can use that.
Is it? Is that good?
More or less. It's
Ah,
good.
so it gives the workspace, is it?
They can do inverse kinematics and all. I have not used it directly, but
Ah.
it is.
No, but does it give nice pictures? Robotics toolbox, huh? Okay, I see.
So it has all these default ones like this cook,
Ah,
and all those things are already programmed, but the other we give the DH parameter values and it will draw it, and then you can do inverse kinematics, forward kinematics, everything.
okay. Hmm. Any other question, Ramji?
No, sir, nothing from my side.
You can send email to the TA, or you can put it up in the forum also if you want. Nitin also, and other students, if anybody else is listening, you can put it up in the forum.
Yes, sir.
Yes.
I see there is one Rajeshri. Rajeshri, welcome to this session. Do you have any question? Rajeshri Rajan. Okay. Are you there? Okay, we need to close at 5:15. Okay, because I think there are other uh, this NPTEL coordinator. No, we have there must be something else at 5:15, right?
Yes, sir.
Hmm. So we need to close at 5:15. So if there are any questions, you have to ask me in the next 2 minutes. Or you can ask me next time. So let me ask a question to Nitin and oh, Nitin has gone. So how do you find the assignments, Ramji? Have you done them?
Oh, yes, sir. Sir, I missed
So-
the I missed the date for a couple of
Ah,
exercises, but yes, it was very useful.
okay. So these assignments are useful, right? That's all
Yes,
I
sir.
want to know.
Yes, sir, yes, definitely.
And it is doable, right?
Yes, sir. Yes.
Okay. Yeah, remember this in NPTEL, the final exam will be based on basically MCQ and MSQ type of questions, but a lot of it will come from the assignments.
Okay. Okay.
Not all, but significant percentage. I think if I'm not mistaken, more than 50% comes from the assignments. So you should do the assignments, then you can do well in the final also.
Yes,
I'll
sir.
share just one screen. So like I'll just show one thing I did in MATLAB. So like these are
Okay. Okay, I'll
To
stop. You can share.
they can see it. Can you see?
No, you have to share. No, I'll
Okay.
stop sharing. You have to share the screen.
Professor, just a general question.
Yeah.
So how is the dynamics and control of mechanical systems different from this course? So I have been through the introductory lectures on that as well. Is that more focused on kinematics uh, and control?
No, the dynamics and control of mechanical system is quite different
Okay.
in the
Okay.
sense that you go into much more depth in dynamics, and we don't look at robotics. So for example, inverse kinematics, forward kinematics are not done there.
Right. Yes.
I hope you probably can see now.
Yeah, now we can see. Yes.
You can,
Yes.
so some, I think KUKA, some robots. So like you can do inverse kinematics and have a visualization as well.
That's nice.
Okay.
I didn't know this. Okay.
Again, it is like MATLAB. So
So MATLAB, oh, by the way, everybody should know you have access to MATLAB, all the modules.
Okay.
In the dynamics and controls course, we do a lot of controls and we
Yes.
do a lot of dynamics, but not very little kinematics.
Okay.
And in this course, we do a lot of, things like you will see Stuart platform, parallel robots, which is not done in the dynamics and controls course.
Model-based control, which you had covered in the DMSF, so that will be in the dynamics control course, right?
No, it'll be here.
Oh.
It'll be here, mostly here.
Okay.
Model-based control is not taught in so much in dynamics. Actually, it's not taught in the dynamics and controls course.
Okay.
Dynamics and control is basic PID and then frequency domain approach and so on.
Thank you, Professor. Yeah, I think.
Okay. So Rajeshri, I didn't hear any question from you. Do you have any question?
No, sir. No, sir.
Okay. So I need to close. So we can close. NPTEL no. We
Thank you,
can
Professor.
close. We can close.
Okay, sir.
We need to close now. Okay.
Thank you.